Or other participants?
You can wait 1 or 2 minutes.
Yes, I can do it. On est en direct là?
Oui, c'est parti.
C'est parti. So welcome to all. I think it's time to start the seminar, and for this new seminar, I think that it is the 11th one in the type of the suite seminar. So we are pleased here to welcome Tivadar and Schaeffer, who are researchers at INRIAS LESM, which is a laboratory belonging to INRIAS institution and the University of Grenoble Alpes. I think that is the right terms for your university. And so you will present here one of your work in progress, but based on the preliminary results and the publications. And the title of your presentation is From Spatial Segregation to Environmental Inequalities. So this is 4 hands papers, but it is only presented by Mihai, and you have 40 minutes for this presentation, and we'll let 20 minutes for the question of the room at the end of the seminar. So as usual, everyone can write his question, their question on the A&R chat, and if you need a clarification point, please indicate it in the chat. So Mireille and Yves, if you agree with that, I'll interrupt you for this type of clarification question. And I can also, or Frédéric can also open the micro to he who asked the question, if it is easier for you and for the questioner. For the R and A&R icon is at the bottom of the page, I think, yes, and close to the icon participants. So I let you the floor for 40 minutes, and if you are in late, I interrupt you. So you have the floor. Thank you.
Thank you, Catherine, for the presentation and for the invitation. So today I will present a work with my colleague Yves Schaeffer from INRIAS LESM Grenoble about how measuring environmental inequalities using spatial segregation literature. Okay, it works. So the measurement methods are for environmental inequalities are needed because there is a context where environmental justice is used more and more often as target in public policies, especially in the United States. And if you are watching the literature on the subject, we can see that environmental justice studies were oriented to unequal exposure to air pollutants phenomenon, but also to unequal access to green amenities. The main methods used in the literature were quite simple and focused only on bivariate statistics, such as bivariate correlations and spatial regressions, but also between group comparisons of means or medians. The problem is that there is obviously a lack in the literature to measure effectively the environmental inequalities. So Boyce suggested in the use of standard inequalities measures, such as Gini and tail indices, for environmental inequality among the whole population, which can be useful to analyze this at a big scales, like international or national scales. But our knowledge, they are not between group environmental inequalities measurements. So we propose to use possible insights from the segregation literature. And why? Because we think that environmental inequalities and segregation are two linked phenomena. Environmental inequalities rise when social groups are differently distributed in space relatively to an environmental variable. So two groups with similar spatial distribution, this means there is no spatial segregation, have the same exposure level to an environmental variable. So starting with this hypothesis, I will present now a little bit the literature on the measures of the social segregation. And Massey and Denton found that segregation is a complex phenomenon, and they propose 5 dimensions of the segregation. First is the evenness, which measures the inequalities in the distribution of group members among the spatial units, the neighborhoods. We have exposure isolation, which measures the opportunity of contact, the probability of contact between members of the same or different groups within neighborhoods. Concentration, it's a new dimension which refers to physical space occupied by the groups. The clustering is a new dimension which takes into account group proximity within and across neighborhoods. So this is meaning that we are crossing the delimitation of spatial units. And finally, we have centralization, where the group distribution, which measures the group distribution around the city center. From this 5 dimensions of the segregation, we won't use all of them because they are not all relevant to the environmental inequality measurement. So we will make also a distinction between aspatial and spatial measures. Why? Because we consider that aspatial measures are unaffected by rearrangement of spatial units of neighborhoods. So if we are taking into account spatial measures, we can use evenness and the special form of the concentration, we will see later. For spatial measures, we can use clustering, which is a dimension very often contested in the literature because spatial evenness could be interpreted as clustering. As Wong said, when the evaluation of evenness incorporates spatial relationship, the concept becomes clustering. So we will use also this type of indices. And finally, centralization. I will go a little bit further to explain this, the indices and concepts that we will use, because environmental variables could be represented in space with 2 different forms. We can have a real data as surfaces, for example, green coverage of each municipality or each spatial unit, but also we can have punctual data where data is represented as points in space. So for the environmental dissimilarity, we will use environmental dissimilarity for areal data, which have 2 forms of presentation, a spatial and spatial forms, and centralization for the punctual data. Now I will present the first type of indices. So it's the evenness dimension of segregation, which is based on segregation curve. Segregation curve finally is a Lorentz curve applied to population groups. We have here the graphic to explain. So in each axis, we have the cumulative proportion of minority respectively of majority, which are ordered by the cumulative proportion of the minority. So we have the segregation curve, and which is compared with the first diagonal. The first diagonal is the situation where the distribution of both groups is identical. And higher is the difference between the curve and the diagonal, higher level of segregation we have between the 2 groups. We have the Gini index, which is represented graphically as the gray surface, the surface between the curve and the diagonal. And we have the dissimilarity index proposed by Duncans in the 55, which is graphically defined as the maximum distance between the segregation curve and the perfect proportional distribution, the diagonal. So this is graphically, mathematically, the dissimilarity index between 2 groups X and Y is computed as the relative differences in each spatial unit between X and Y. And as property, the dissimilarity index is between 0 and 1. Can be interpreted as the share of the minority group that would have to move to achieve the even distribution. So for example, if D is 0.5, this means that 50% of the minority group should move to achieve an equal distribution between X and Y. So this is the basic dissimilarity index. And we will use, not conceptually, but only as methodology, an aspect, an index from concentration dimension of segregation, which is the delta index. Delta index measures the concentration, the space occupied by each social group, but it can be interpreted as the dissimilarity between the distribution of a group of population and the distribution of land. So its definition is the sum between spatial units of the relative difference between the population and the surface or a real data. So this is interesting for us because we can see that we can compare finally the relative distribution of population and a real data, which is the case for a real environmental data. And the interpretation would be the same, the share of the population that would have to move to achieve uniform spatial density. In our case, we will apply now this concept of evenness to a real environmental data, and we define the environmental dissimilarity index, ED, between X, a population group, and A, an amenity, as the sum of the relative difference between the distribution, relative distribution of the population and amenity within spatial units. As usually, its values are comprised between 0 and 1 and can be interpreted as the dissimilarity of spatial distribution between a population group and a real environmental amenity or dissimilarity. Just two examples, theoretical example, that each circle represents an amenity surface and gray-black is the population distribution. So we can have a null dissimilarity when all population and also the amenity are concentrated in a unique spatial unit, or the same result if they are distributed proportionally within spatial units. And on the contrary, we have a maximum dissimilarity between the population and the amenity when they do not share any neighbor. So we have the population which is completely separated in space from the environmental variable. We are interested about the between group inequalities, so we define it as the differential of environmental dissimilarity. So delta ED finally is the difference between the dissimilarity of the first group and the second group, which can be computed mathematically like this. As properties, it varies between -1 and 1. And oops, what is really interesting as property is the fact that its absolute value is limited by the level of the dissimilarity. And this, we can interpret this alternatively, such as that social segregation is a necessary but insufficient condition to environmental inequality. Why that? Because if D, it's null, so if we don't have segregation, automatically the between group environmental inequality will be also null. So if we want to have a positive delta ED, we need a positive D. So the social segregation, it's necessary, but it's not sufficient because for a positive D value of this, of course, we can still have a null delta ED. The problem with this index is that it's completely aspecial. So we have here up in the slide a situation when the delta ED, the aspecial form of the between group dissimilarity, environmental dissimilarity, it's maximum, it's 1. And we can see the fact that if you take into account the spatial interaction, in the second situation, the population is closer to the amenities. So it's not, it's an obvious limit of this index, especially when the spatial units, the neighborhoods are small. So the interaction could occur between spatial units. A solution is to use the Morris adjustment, who was a geographer and who worked on the subject in the early 90s. He considered that spatial interactions appear when two spatial units or neighborhoods are adjacent. So we are using the contiguity matrix, which values are 1 if two neighbors are contiguous, adjacent, and 0 otherwise. And then after that, I will use the generalization of spatial interaction when we consider different levels of contiguity, not only first level of contiguity, but kth level, kth order contiguity matrix. This is really, it's interesting to use it, especially when these spatial units are really small. And then we can consider that the spatial effects don't appear only in the strict first order neighborhood, but also for the second and third and so on. So the adjusted version of dissimilarity index is computed as the dissimilarity index reduced by spatial interactions. And spatial interactions, we have several points. We have a distance decay function, Fk. We have Wij, which is the special weight matrix, and delta Ieg, who represent the interaction, special interaction between groups in the special units Ing. The distance decay function Fk is defined by continuous order k with a decreasing function who starts in 1 and finished in 0, limited in 0 when k is infinity. The special weighted matrix is defined as kth order contiguity matrix, and special interaction terms, which are defined here, are computed as the relative difference of the share of the group X in each special unit. The problem is for this term to use it to adapt it for environmental dissimilarity has 3 points. First, if we want to adapt it for environmental situation, this means that we have to make the sum between a population, xy, and a real surface. And it doesn't make sense because they are two completely different measures. Secondly, this term is also influenced by the size of the population, so by the measurement unit, which could be a problem as the real surfaces can be computed, expressed in square meters, square kilometers, so it shouldn't be influenced by that. As we can see in this graphic, I propose alternatively to use the dissimilarity index between group X, Y densons in a subarea formed only by two special units, Y and G. And if we compare the two measures, we can see that in the red line, we have strict linear relationships, and when we change the proportion of the groups, so the size of the groups, we can see that delta is changing. So now we can adapt it for environmental dissimilarity, where we can define it in the agency of k order as the environmental dissimilarity diminished by special effects, where special interactions are defined as environmental dissimilarity between X and A in the subarea form only by Ing. We can also mathematically show that this value is quite simple to compute. Then we have our target index, which is the differential of environmental dissimilarities, which can be computed in a quite similar way as Morris generalized index. And as properties, this time we can see that this delta ED with adjusted versions it's limited by the level of segregation by dxy, but is increased by the aggregated positive special interaction term. This term is positive because we can show that inside the bracelets it's a positive term. So this condition is less restrictive with stronger special interactions. Last type of adjustment that we can make on the dissimilarity index were proposed by Wong still in the 90s, and which are available for first order contiguity metrics only. And he defines special interaction between contiguous special units as proportional to the length of the shape boundaries. So a weighted special matrix, it's equal to the boundary matrix. This version of the index is very interesting when we are using rather bigger special units such as IRIS data or municipalities data, which have different shapes and forms. This is why he proposed a second version of the index, where he included also the shape of special units as the perimeter area ratio. So the special matrix is not only depending on the borders, but also on the shape of the special units. Some theoretical examples, as I showed before, we have two situations when a group is closer to the amenity than a second one, but still they do not share the same special units. And we can see the special form of the index, it's 1, complete separation. But if we take into account first contiguity, for example, here we have a first interaction that appears for the second case, and then the special interaction reduce the level of the index as the level the contiguity matrix order increases. Now I will present a second type of indices, which are based on the centralization concept, which can be applied to punctual environmental data. So the first centralization analysis were proposed still by Duncan in the 1955, And they computed the monocentric relative centralization index, which measures the localization unevenness of two groups around a specific point, the center. So this means that it is a particular form of the Gini index by ordering special units according to their distance to the center. So for the standard Gini index, we were ordering special units according to the proportion of the minority. Now we will ordering by the distance to the center. This index can be applied to inequality around a specific environmental amenity and generalized for several amenities, which is using the polycentric centralization form, considering the distance to the nearest point. So environmental relative centralization index is computed, as I explained before, as the surfaces between the segregation curve and first the diagonal. And mathematically it can be shown like this, where x and y are ordered by the distance to the closest environmental variable. As property, the relative centralization will be between -1 and 1. A negative value implies that that x group is located closer to the disamenities than the y group, and for a positive value is the reverse. And the second interesting property is, once again, its absolute value, it's limited by the Gini index, bounded by the Gini value of the Gini index. So once again, the social segregation is a necessary but insufficient condition of the environmental inequality. Some theoretical example, we have, for example, case A with a cluster of the minority located in the northeast. Each cell of the area is representing the neighborhood or a special unit. And we have a monocentric environmental data. Obviously, the relative centralization is maximum 1. If we add, for example, a second point with a localization of this amenity or amenity, of course, the centralization will diminish for the minority compared to the majority. And we have here some other interesting examples. And the last point about centralization, we introduce the concept of centralization with spatial constraints, because we can take into account a situation where the influence of a centrality is limited. Why that? Because we can assume that, for example, a risk industrial site cannot have an impact for someone who's located really far away. So we can introduce these spatial constraints as k nearest neighbors or a certain distance of influence. And we can see here that, for example, for the first case, if we increase the distance of influence, the index is not, in this case, is not changing. But in other cases, of course, it changes as we take into account only some special units around the point. Now I will paste to a case study on Grenoble metropole, which was the object of a paper we published 2 years ago now, almost 2 years ago, in ecological economics. When we analyzed the environmental inequalities with this situation with areal and punctual data. For the areal data, we used the percentage of green cover. And for the social distribution, we had the percentage of low income in space. Each cell represents 200 the dimension is 200 meters of each cell. And as we can see graphically on these maps, there are obviously clear correlation between the green distribution and the low income distribution. Just some numbers in the study area, there are almost 200,000 households, with 18% being low-income households. If we use the standard, the bivariate analysis, the bivariate correlation shows a negative correlation between the proportion of poor and proportion of vegetation. So this means that there is an inequality between the poor and the vegetation, but is not measured. This is confirmed by basic multivariate regression with negative significant values of the coefficient and an R-squared adjusted of 0.4 almost. But now we want to measure these environmental inequalities using our methods. So first, we computed the social segregation levels in the area. We obtained a Gini of almost 0.5. This minority is 0.33. This meaning that 1/3 of the poor households should move to achieve an even distribution in the area, and special evenness of first order, for example, the Morris dissimilarity, which is of course reduced from 0.33 to 0.26. And now we computed the environmental dissimilarity index for the poor, for the non-poor, and the differential between the two groups. And as we can see also graphically, we see that environmental dissimilarity is higher for the low-income households. It was what we expected. And what is interesting is the fact that introducing special interactions reduce the environmental dissimilarity, but also the differences between groups in absolute values, but also in relative values. Now, an important step is to introduce statistical significance test, because to make robust analysis, and for that we use the randomization test procedure as I develop for segregation analysis. Three types of tests can be used: permutation test, where the distribution of the test statistic under the null hypothesis is obtained by calculating all possible values of the statistic under different rearrangement of the labels on the observed data. The problem is that when the number of combinations is too high, we will use an asymptotically equivalent test, which is approximate or random permutation test, or more known as Monte Carlo simulation. A second type of analysis is bootstrapping, which consists in resampling with replacement from the data set. And finally, jackknife simulation, where simulated index distribution is obtained by systematically recomputing the statistic, excluding one observation at a time for the sample set. We will use especially two methods: Monte Carlo simulation test for global analysis, which allows us to test if the observed differences between environmental dissimilarity values do not reflect random differences in the spatial distribution of social groups. And we will use jackknife simulation for local analysis to identify special units whose removal will result in significant decrease or increases in environmental inequalities. I will explain all this for be more clear. So for the Monte Carlo simulation, there are 4 steps. First, we make simulation of n random distribution of population, and it's usually used as it's around the number -1 to make easier computation. And for each simulation, the households are randomly assigned to residential location, the neighborhoods or special units, with a proportional probability to the residential capacity. We use, for example, the number of observed households. Then for each replicate, we compute the index, which gives us finally the simulated reference distribution. Now, having a reference distribution, we can compute a pseudo p-value that is equal to 1 minus the relative rank of the index, observed index, in the reference distribution. This method was employed first by Anselin for special indexes. And then pseudo p-value can be interpreted as a statistical significance test of the hypothesis that the index is the result of random processes. For our case study, we have the results of the Monte Carlo simulation. For k equals 0, this means with no interaction, we have the value of the index for the poor, the similarity index for the poor, for the non-poor, and the difference. We have the mean computed in the simulated distribution, the rank, and the pseudo p-value. The most interesting is to see these results graphically, because it's more easy to understand. For example, for our case study, for k equals 0, this means no interaction. For the poor, the value of the observed index, the computed index, is much higher than the distribution of the random processes. So we can conclude that it's statistically significant. In the same time, for the non-poor, we have a distribution which is doesn't coincide with the location of the compute indexes. And as we can see, the two effects, now we will go together because it's the poor minus the non-poor. It will have a significant result. For k equal 1, this means that we take into account first order contiguity. We can see that the poor value, it's significant, but for the non-poor, the observed index, it's inside the random distribution, so it's not significant. It could be the result of a random process, but as the first term it's significant, and when we make the difference we obtain, of course, a significant effect. Now I will present the jackknife simulation, which has several steps. First, we simulate simulation of F, a big N random distribution of population, where the special units are successively withdrawn. So the number of the simulation equals the number of neighborhoods or the number of special units. So for this, each simulation, we take out one neighbor, we compute, and like this, we have N random distribution. For each replicate, once again, we compute the index to obtain the simulated reference distribution. And then we will make an outlier analysis in the tails of the distribution. Why? Because each outlier is attached to a particular simulation where one special unit has been removed. The methods that we can use for outlier definition, they are box plot method, which I will present later, scores methods, and median absolute deviation method. The outlier special units represent finally the hotspots in the area, more precisely the neighborhoods with greatest impacts on the index. And what is interesting, that they can be mapped as is a local analysis. And here are the results. For example, here we have the box plot representation, and we find the outliers, the points that are at least twice the difference of the standard deviation compared to the mean. And these outliers corresponds to some special units in the area. We made a difference between the blue and the red, where the threshold 0.3 is given by the box plot analysis. And we have the representation for the environmental dissimilarity for the poor and the difference between the poor and the rich. I won't go inside the explanation here, but as we can see, we can plot the neighborhoods that we have a big impact, a significant impact of the index value. To understand better, for example, this means that if we take out these special units, the index value will decrease strongly. So if we put it back, this means the index is increased. And now I present the results on the study case using potentially dangerous services sites in the metro area. It's about 14 industrial sites located in the Grenoble area, and 9 of them being considered high-risk industrial sites. We computed the environmental centralization for 2 cases, for all service sites and only for high risk, and we obtain a positive value. That means that poor are closer to the service sites than the non-poor, especially for the high risk. This is the graphical representation of the index. So we have the cumulative proportion of the poor and the non-poor, where the special units are ordered by the distance to the service sites. And as we can see, for the surface between the curve and the diagonal, it's higher for the high risky sites than for the service, which is confirmed also mathematically. If we introduce local constraints, we have the index distribution from 100 meters to 15 kilometers with a step of 100 meters for each simulation. And we can see that for a distance superior to 10 kilometers, the index, the constraint version of the index converges to unconstrained value. But for intermediate values, they are complete complex pattern. Sometimes it can change its value, its sign. For the environmental centralization, we can make the same robust analysis and significant test. Global analysis with Monte Carlo's test confirm that the environmental inequality is significant, as the observed value do not reflect random differences in the population distribution. And the local analysis with outlier test can help us to plot the neighborhoods that have a significant impact of positive here or negative impact on the index. Last part, I will present the R package called SEG and INEQ because it's a statistical package developed in R software, which is already available on CRAN. It was published last year, several months ago, and CRAN is the official server of R software. And this package compute only 4 functions, but it's all we need to if we want to use all this methodological development. We have ED function, which that computes the environmental dissimilarity with only two obligatory parameters. X is the vector of the population distribution, the number of the people on each spatial unit, and A is the amenity distribution. And then we have a series of optional parameters, which depends on the version of the index, the standard, a special if you want, or different special versions. And how to use it, I will give first we need to charge the package in our environment. And then I will use a theoretical example from Oasis R package. It's a package I developed for segregation analysis. So I will use data seg data. And this example corresponds with this situation when the gray points, the gray area represents the localization of the amenity, and white surfaces represents the distribution of the population. As we can see, there is a complete dissimilarity between population and amenities. So if we compute ED function, the standard version, we need only to give the vector of the first variable and the vector of the second variable, and the result is 1. If we want to compute something more complex, we can add, for example, the version, the contiguity, and then we need to introduce geographical information such as shapefile or R spatial object. And for example, for contiguity, we can define contiguity using Queen criterion or Rook criterion. And here we have the result. The same situation, for example, we can use adding also the more distant contiguity matrix, so K equals 3. And also we can compute the version with boundaries or shapes. And as I give this example because as in this example, the shape of the special units is identical, the boundary version of the index have the same result as the contiguity. We have EC function, which computes environmental centralization. In input, we need a matrix with a distribution of 2 populations, so a matrix with 2 columns, and then different possibilities to introduce the geographical information as distances or giving special objects or shape files. And as example, as you can see, EC function is quite easy to use. We need to introduce the matrix with a population distribution. And here, for example, I use the distances for a theoretical example from Oasis R package. And finally, we have the resampling test and plots functions. The env resample test function allows us to make all these tests that I presented before, all 3 types of tests. And then environment resample plot, environmental sample plot that can plot all these results. And I now have the conclusions. With this work, we had several important contributions to the literature. First, we developed robust special methods to measure between group environmental inequalities related to social segregation. Then we conducted an empirical analysis on Grenoble, France, which resulted with a paper published in Ecological Economics. And we developed an R package called SEG and INEQ, which allows easy application of our methodology for different case studies. And the next steps, what remains to done, we need to conduct an empirical analysis of the environmental inequalities in whole France. And secondly, this analysis will allows us to see if there are empirical connections between environmental inequalities and social segregation, testing the hypothesis that the more segregated agglomeration have also the highest environmental inequalities. Why we want to test this hypothesis? Because even if social segregation is it's only a it's a necessary but not necessary condition, it gives the highest level that is environmental inequalities can achieve. So statistically, there is probability that to be higher in the areas with a high level of segregation. Now I see that there was a question I didn't see before, sorry. So can this indices help to reduce social segregation by adaptive spatial distribution of green amenities, future planning decision? Are this indices sensitive to the type of amenities, negative for pollution, positive for green areas, for example? And finally, if we consider recent planning recommendation of growth control, no mortification, for example, what can we expect for spatial segregation? A very interesting question. So I will start with the first. Can these indices help to reduce social segregation by adapted spatial distribution of green amenities? This is linked with the third. I think that it's rather the reverse situation. It's the environmental inequality is the result of the social the segregation and not reverse. So it's if we want to fight against environmental inequalities, we can use measures that will reduce social segregation, but the reverse is not sure. It's not sure that it will work, as even the mathematical demonstration shows that the environmental inequality are limited by the social segregation. So, and it was. Are these indices sensitive to the type of amenities? No, they are not sensitive of the type of the data. And so another question, it is possible to have an interpretation of the spatial dissimilarity indicators, not in terms of the percentage of amenities that should move, but in terms of the percentage of amenities that should move. This is an interesting question. And yes, we explain the results like this because we consider that it could be easier as interpretation. But yes, if we change the amenity distribution, if, for example, we make a new park in some sectors, or of contrary, we are industrializing, we are reducing green spaces, we will change the spatial dissimilarity indicators, all of them. So to reduce environmental inequalities, we have two solutions. One, make the people move, or secondly, change the distribution of amenities or of risk. And of course, normally this will change the condition for location choices of the households. So this can change also the social structure of the city, then the social segregation.
Michael?
Yes.
What is your feeling about your last question? So the more segregated agglomerations have also the highest environmental inequalities. What is your feeling about that?
Normally, we should find a correlation between segregation and environmental inequality. Why? Because inequality are limited by the segregation. If segregation is higher, inequality have higher limits of distribution. So, for example, if we are in we take two urban agglomeration, one with 0.3 dissimilarity and the second with 0.6 dissimilarity. So the second agglomeration is much more segregated. This means that the environmental inequality could take a value between 0 and 0.3 only for the first, and between 0 and 0.6 for the second. And even with a random distribution, normally we can find, we should find higher level of environmental inequalities in more segregated areas. But this is hypothetical. We have to check that.
But does it mean that you can compare your dissimilarity indexes between cities, or it is intrinsic one value for one cities?
It can be used between cities, but one of the limits of segregation measures that sometimes they are influenced by the size and by the number of the special units. So the cities should be at the same size for the comparison. In time, of course, in time the population evolution is too small to have a significant impact of the indices, but it depends on the index, how it reacts, of course.
And I have also one question, but perhaps there is more questions or another question from the room. So I have another question concerning what you know about the BTZ model. So you have environmental or green amenities, but you have also patrimonial amenities. And so you only consider green amenities, blue or green amenities, that is environmental amenities, or can you consider also semi-endogenous amenities like patrimonial amenities, services, so all amenities that are provided by, in some sense, a certain level of urbanization. And urbanization is opposite to green amenities in some sense.
What is interesting for this methodology used from social segregation analysis is that can be applied for very wide situations. So if we have data as a real data, we can use it. If we have data as punctual data, we can use it. And even as count data, because if it's count data, we can approximate it as a weighted data on each point. So yes, I gave an example because the objective of this paper is to analyze environmental inequalities, but yes, it can be used, for example, to measure the dissimilarity between a group population and services distribution. So, for example, we can answer the question if a group is more segregated compared to the services than another group, more dissimilar distribution.
Okay, so thank you very much for your very interesting presentation and papers. You said that you developed the R package.
Yes.
So everybody can use this R package. Okay.
Yes, it's quite easy we try to develop R function that answer all the situations. So you can use the very easy version of the function with no big parameters, but also we have the possibility to enter the details and to make very complex analysis. So I invite you to use our packages, of course.
Okay, and is it also included in your OASIS?
Sorry, I don't
OASIS tools.
Or...
Yes, so you can speak about OASIS perhaps. I think that I can't hear you anymore. So
we lost Mihai.
Yes, we lost Mihai, but
I take the floor.
Yes, and there is another question for you, Yves, because we lost Mihai. So is there a link between segregation indicators, social and diversity social indicators? So you have this question on the conversation, on the chat. So perhaps you can read the question directly.
Yes, is there a link between segregation indicators and diversity indicators? I think there are links between some segregation indicators which uses entropy measures, but that's not the kind of indicators we used in our work. But I'm not totally sure of what I'm saying here, but I think maybe there are some links with entropy indicators which are used also in segregation literature. Maybe Mihai, you can
yes,
complete.
They are, for example, eveness segregation indices that they are using entropy concept and also social composition. But we choose the indices that are not affected by the size of the groups. This is why dissimilarity index, for example, is really interesting because it's relative distribution. And by relative distribution, this allows us to use different type of data and are not influenced by the size of the groups. For example, we could use also proximity indices, which are another type of social segregation indices, but they are not compatible with exactly with this point of view.
Okay, thank you very much. So, and you said that the future work was about empirical application. Oh, and what about first results? For example, you showed some maps about the agglomeration of Grenoble. I don't remember your maps. And I have another question about multicentrality. That is the organization of the urban area. For example, it is Grenoble Metropole. So in the middle of your map, I think that you have all the most denser parts of the agglomeration. It is the city of Grenoble, for example, or it is wider than the city of Grenoble.
This is the perimeter of the metropole, I think, in this work, or was it? So in the middle, there is a town hall, which is put on the map. You can see
here the star
of the city of Grenoble, but it's wider than the
okay.
It's here.
Town.
Okay, so this is, in some sense, it was my question about the relation between negative disamenities, negative amenities like risk, for example, pollution or risk, and positive amenities. Because my question was, if you replace a Seveso enterprise, for example, by a park or a green area, is it the same thing?
We cannot answer this. We didn't analyze this indirect relation between two types of amenities. But we could try, I think, to see if there is some connection, what it will be if we, as you gave as an example, change a risk site with a positive amenity, if they will have a change. But for example, I think we should check the results of the jackknife simulation for both cases, because if we check the jackknife simulation and if we found that the same special units are significant for the centrality for Seveso, respectively dissimilarity for green spaces, in this case, yes, it will change. But if they are not significant, different, they are not outliers that will be significant. In this case, even if we change, it won't change a lot. But if we should check the, I don't have the map with the location of the Seveso. Ah, yes, here. As you can see, some of the points are close enough to the Seveso here, for example, and here especially for the higher risk points. There are chances that we will find the same special units that are significant for both cases. But this is what we should search for.
I open my macro, so thank you very much. We have
you.
times for other questions. I think that everybody are waiting for further results and empirical results, because we have many planning regulations at the moment that want to stringent artificialization and perhaps to rebuild cities, so replace some housing, bad housing, by modern housing, or by or replace them by green open space, for example. So I think that your contribution helps to measure, to simulate, for example, to simulate if you replace some building by some park.
Yes.
And also according to biodiversity conservation, for example, because we need some areas for biodiversity and also some corridors to help displacement of species, for example. So I think that it could be interesting also for this new development and new planning regulation according devoted to green amenities.
I think that our methodologies can be used in two different situations. One is to answer to some political decision, as you said, for example, to simulate the impact on social segregation, respectively environmental inequalities. But also we can make it reverse with jackknife techniques. We can find the hot neighborhoods in the city where we should focus our policy. For example, these neighborhoods have the most impact for the segregation or for the inequalities. So it could be working in two senses. Yes, simulate some policies, but also proposing a solution to the policies.
Okay, so thank you very much.
Thank you.
Do we have other question, or can we consider that the seminar is closed, can be closed? Frédéric?
Oui, je pense que non, c'était très, très intéressant. Ça m'a remis dans des choses fortes. Oui, oui. Non, c'était très, très, très intéressant.
Oh, merci.
Vous avez fait, oui, oui. Sur ces questions-là. Puis sur les méthodes, ça faisait assez longtemps que je n'avais pas entendu parler de méthodes de jackknife, en fait.
Ah, moi, j'étais obligé, moi, je n'ai pas entendu de ça non plus, mais quand j'ai publié l'article sur Oasis Air, dans les reviewers, au début, on n'a fait que des tests de Monte Carlo, voilà, simple, on fait des simulations, on teste si c'est aléatoire ou non, et hasta la vista. Mais dans les retours, ils ont dit, bah, non, si vous faites un outil, des trucs comme ça, il faut faire du jackknife, de bootstrapping, randomization, test toutes les versions, etc. Et donc, du coup, voilà, on était obligé de développer ça. Et finalement, c'était super utile et super intéressant parce que ça a ouvert la voie pour des nouvelles publications derrière. Par exemple, ce qu'on a fait ici.
Oui,
peut-être on peut annoncer le prochain séminaire, parce que ça va être l'heure de la fin, Lionel.
Yes.
Next seminar can...
But I don't remember.
Ah.
I just take a look.